Alright, so here we have a force on an inclined plane problem, and I'm going to work through this just like I worked through all the other ones, and hopefully this gives you a good idea of what we're looking for on test 1 and just the thought processes behind solving one of these problems. So the first thing to note is in the problem statement we're given that this is an open tank, which means the pressure at this point at the top of this tank is 0. From then we are asked to draw the y-axis, which in this case goes straight along the edge of this gate here, and then we're asked to find y bar. Y bar is the distance from the water surface to the centroid of whatever gate we're talking about. In this case, this gate is rectangular, which means it is half the distance down. That's where the centroid of this rectangle is. So, in order to do this, it's simple geometry. We have this triangle right here with 60 degrees here, and then we are trying to find this distance here, which is y bar, and so that means that's y bar, and this would be 3.1 plus half of 6 right here. So we will have 6.2 feet, and in order to solve for y bar, we just divide 6.2 by sine 60, and we get a value of 7.2 feet, and that is the value of y bar. Now we have to determine the dimension h, and all that means is to find this distance right here. So h is going to be, if we just draw this triangle real quick, we have 60 degrees with 6 feet, and then this is h. So h is just 6 divided by sine 60, which gives us a value of 6.93 feet. Alright, so that's part B completed. Part C asks us to find the force on this gate that all this water is causing it. And to do that, we have the force on an inclined plane equation. This is given on your equation sheets, and that equation is as follows. The force is on an inclined plane is equal to gamma water times y bar times the sine of the angle times the area of whatever we're talking about here. So if we just plug all that in down here, we have F equals gamma water times y bar, which is 7.2 feet, times the sine of 60 degrees, times the area, which is 4 times 6.93, which is the area of this gate right here. And we get a value for F to be approximately 10,700 pounds, and that acts perpendicular to the gate right there. So that is part C completed, and now we're asked to find the distance YCP minus y bar. Now remember that if we have this gate right here, that's terrible, and this is the centroid of it, the center of pressure is just a little bit below there, and this distance here is y bar minus YCP, or excuse me, YCP minus y bar. That's this distance here. So we know what y bar is, and YCP is equal to y bar plus I over y bar times A, and I is the second moment of inertia, or you can think of it as the area moment of inertia. And this is just a geometrical property, and for a rectangle it is given by this right here, which is 1/12 base times the height cubed. The base is always the surface that is parallel to the water surface, and h is going down in the z direction. So if we just manipulate this equation a little bit, we get ycp minus y bar is equal to I over y bar a, and this value right here is what part D is asking for. So if we just plug in our numbers, ycp minus y bar is going to be equal to 1/12 base times the height, and the base is going to be 4 in this problem, times the height, which is 6.93. That's cubed, divided by y bar, which is 7.2 feet, times the area, which is 4 times 6.93. Some of these numbers will cancel out. This 4 and this 4 will cancel out. This 6.93 and one of these 6.93s will cancel out, so we'll be left with 6.93 squared on top. And so moving all this down, we will get 6.93 squared over 12 times 7.2. And that gives us a value of 0.556 feet. And in this little diagram right here, all that means is the center of pressure is about half a foot below the centroid of this body, of this gate. So that's our answer for part D. Now we need to know, or now we need to figure out the force on the very bottom of this tank, right, or on the very bottom of this gate, that is required to keep the gate closed. Because all this water in this tank right here is all pushing on this gate, trying to get out, and we need to find out what the magnitude of the force needs to be in order to keep this gate shut. So to do this, we have to take we have to do a moment analysis on the hinge. So the sum of the moments about the hinge have to equal 0, because we're trying to figure out how to keep this thing shut. So all the moments need to be 0 in order to have it not swing open. And we're going to say clockwise is positive. And again, just like the other problems, doesn't matter if you choose the other way as positive. You just all the signs for this next part will be negative. And this problem, if we draw a free body diagram of this gate, right here, we have a force on the bottom, that's just F bottom, and then we have the force of the water, we'll call that FW. The total length of this gate is 6.93, and then the distance to FW is going to be half of that distance, which would be the centroid of this thing, plus 0.556 right here. So that's going to be 6.93 over 2 plus 0.556. That's this distance right here. So this F bottom is trying to rotate this gate counterclockwise, so that will be a negative F bottom times the moment arm, which is 6.93 feet, plus a positive force for the water, because it's trying to rotate about this point right here, it's trying to rotate that clockwise, times its moment arm, which we said was 6.93 over 2 plus 0.556. And we can do some simple math, some simple arithmetic. We can also plug in 10,700 for FW. And we will get a value for F bottom to be 6,210 pounds. So what this means is this force right here has to be 6,210 pounds right there in order to have this gate not swing open due to all the water inside here. Now this problem was fairly straightforward in my opinion. This is a very simplistic form of this problem. Another way that we could do this is pressurize this tank. So your Y bar, in the way that we did it, was simply the distance here. But if this was pressurized, we would have an equivalent water surface, which would be somewhere up here. And you would have to add this distance in your Y bar. Another thing we could do is we could make this have a different fluid. So we could say this is oil in this section, and then this could be open up here, so this could be the top, or we could have this be closed and pressurized. This is probably the hardest that this could get. Actually, no, if we wanted to make this even harder, we could make this gate some kind of different shape. We could make it a trapezoid. We could only have half of the trapezoid. We could make that gate a whole bunch of different shapes. But yeah, hopefully you guys understand at least the process to do this problem. Yeah, hopefully it helped. If you have any questions or concerns, please email me. Test is tomorrow. Good luck on it, everyone. Yeah, happy studying.